Alright, continuing with this series of videos, examining, in perhaps a critical way, the claims made by conventional physics as presented by Professor Lewin at MIT University and such. So, yes, quite a disagreement here about this paramagnetic, ferromagnetic, and what kind of field is created. So let's play this through, but I don't know if we're going to get anything like resolution here.
So in all cases, whether we have diamagnetic material or paramagnetic material or ferromagnetic material, the magnetic field inside is different from what the field would be without the material. And what the field would be without the material we've called external field, I've called it vacuum field. And in many cases, but not all, next lecture I will discuss the issues of not all. In many cases, but not all cases, is the field inside the material proportional to the vacuum field. And if that is the case, then you can write down that the field inside is linearly proportional.
So, this is kind of a confusing way to say things. So he's saying the vacuum field is the field that without the other disturbance, and yet somehow the field inside, when there is a disturbance with another magnet, is somehow still proportional to some vacuum field or some state it was in before it was disturbed. I don't know. I can't make much sense out of that. Sorry.
So this is the field inside the material, regardless of whether it's diamagnetic or paramagnetic or ferromagnetic, is proportional to the vacuum field. I will write down vacuum for this. And this proportionality constant I call kappa of m.
Alright, so this is just really saying that you can only magnify it a certain percentage. So you're taking a thing that exists and you're saying how much has it grown. So, but I think this really depends on the circumstance. So again, like the coil of wire, you're ending up with the internal reflections, that's the growth. But clearly there's a proportion to how much wire there is and how many turns there are. So, yeah, so there's not much to say about that. So the argument is this: there's just this kappa is just going to be a constant for really the conductivity of the material, or its capacity to hold charge, or it's just a way of saying that each material has a unique capacity to create the circumstances that will allow it to become more magnetic.
Bohr calls it K of m, and it's called the relative permeability. And so now we can look at these values for the relative permeability, and we can immediately understand now the difference between diamagnetic material, paramagnetic material, and ferromagnetic material. Since in the case of diamagnetic material and paramagnetic material, the B field inside is only slightly different from the vacuum field.
Yeah, unfortunately we can't see the whole thing. So the top of the list is, you got these numbers, minus 1.7 to 10 to the 8th, which means it's unmagnetic almost. And then you have, that's the diamagnetic, it's just a very low capacity to become magnetic. And then paramagnetic's going to be still strangled numbers, but I think it's kind of a deception in how they would measure it. But regardless. And then ferromagnetic's much higher, but paramagnetic, obviously in the right circumstances, is a pretty strong magnetism.
It is common to express kappa of m in terms of 1 plus something which we call the magnetic susceptibility, which is psi of m. Because if it is very close to 1, then it is easier to simply list psi of m. And let's look at diamagnetic material. Notice that these values for psi of m are all negative, of course. They have to be negative, otherwise it wouldn't be diamagnetic. It means that the field inside is slightly, a hair smaller than the vacuum field. Because these induced dipoles oppose the external field, remember. That's nothing to do with Lenz's law, but they oppose it nevertheless.
So, again, the fact of whether it's opposing or not opposing, to me, doesn't mean much in terms of the fact that you're making it more magnetic. So, again, so this is a weird argument of whether or not it's creating a magnet that's pointed north-south or a magnet that's pointed south-north. I don't think it's important as finding out how much pointing it can do, how much magnet it can create.
And so you express it in terms of the magnetic susceptibility, and so you have to take 1 minus 1.7 times 10 to the minus 4 to get kappa of m, which is very close to 1. If now you go to paramagnetic materials, the minus signs become plus. Again, the numbers are small. But the fact that it is plus means that inside paramagnetic material, the magnetic field is a hair larger than the vacuum field. But now if you go to ferromagnetic...
So the field's inside, I think it's just it's voltage when it's inside, frankly. It's better understood as voltage, pressure, and plus or minus voltage. It's better understood as voltage than it is understood as in the raw form of magnetism, because it's only magnetism when it's expressed to the world and some magnet can detect it. It can affect the compass. Otherwise, it's not, it doesn't mean anything until it gets out of the substance.
Magnetic material. It is really absurd to ever list the value for psi of m, because psi of m is so large that you can forget about the 1, and so psi of m is about the same as kappa of m. And so you deal there with numbers that are 100, 1,000, 10,000, and even larger than 10,000. That means that if kappa of m is 10,000, you could have a field inside ferromagnetic material that is 10,000 times larger than your vacuum field.
So you can increase it by 10,000, which is, a huge number. But obviously that's sort of real-world experience, is that you put a piece of iron in a coil and it goes from being non-magnetic to being very strongly magnetic.
Next lecture I will tell you that there is a limit to as far as you can go, but for now we will leave it with this. So paramagnetic and ferromagnetic properties depend on the temperature. Diamagnetic properties do not depend on the temperature. So at very low temperatures, there is very little thermal agitation, and so you can then easier align these dipoles, and so the values for kappa of m will then be different. For ferromagnetic material, if you cool it, you expect the kappa of m going up. So you get a stronger field inside. So it's temperature dependent. If you make the material very hot, then it can lose completely its ferromagnetic properties. What happens at a certain temperature, that these domains fall apart, so the domains themselves no longer exist. They annihilate. And that happens at a very precise temperature. It's very strange. That's also something that is very difficult to understand, and you need quantum mechanics for that too.
Yeah, I don't think you do. But anyway, so yeah, obviously temperature creates a bunch of movement. And now when it cools, they can cool in a different position. So it randomizes things that weren't randomized before. And I guess in theory, because of the subtleties of how weak each little individual magnet is, it's easy to create chaos. Just as it's easy to create arrangement, with a little bit of an external help.
But at a certain temperature, which we call the Curie temperature, which for iron is 1043 degrees Kelvin, which is 770 degrees centigrade, all of a sudden the domains disappear and the material becomes paramagnetic. In other words, if...
I would say I'm not sure whether it becomes paramagnetic, and it seems quite obvious that it doesn't, because by either standard, he'll do an experiment that sort of demonstrates, but we'll see. I'll wait till the experiment.
Ferromagnetic material would be hanging on a magnet, and you would heat it up above the Curie point, it would fall off. It would become paramagnetic, but paramagnetic material in general doesn't hang on a magnet, because the forces involved are quite small.
So again, the forces involved aren't quite small. Paramagnetic can create quite a strong effect, just like dropping the magnet through the piece of copper, all those examples. The effect is dramatic in some cases, and certainly the maglev trains is pretty dramatic effect, pretty strong magnetism being created.
And the change is very abrupt, and I'm going to show that to you with a demonstration. I have a ferromagnetic nut. It's right there, you will see it very shortly, and this nut or washer hanging on a steel cable, and there is here a magnet. I don't know whether this is north or south, it doesn't matter. And here we have a thermal shield. And so this washer is against the thermal shield because it's being attracted, it wants to go towards the strong magnetic field. It's ferromagnetic. So it will be sitting here. And now I'm going to heat this up above the Curie point, 770 degrees centigrade. And you will see it fall off. And when it cools again, it goes back on again. So I can make you see ferromagnetic properties disappear. And let me make sure I...
Sort of makes sense. I mean, when you get up these temperatures, also the steel becomes malleable, where you can smash it and hit it with a hammer and move all the little sections of it and the pieces of it in different new arrangements. So obviously that logically makes sense. But it also makes sense that when it's hot, if you expose it to a very strong magnetic field, that as it cools, it will probably cool, retaining that some orientation to that strong magnetic field you cooled it in.
Have the proper settings. I see nothing. I see nothing. But there it is. So here is this nut. And here is this shield. And the magnet is behind it. You can see it. It's right there. And so it goes against it, right? It goes just towards the magnetic poles. It goes into the strong magnetic field. The magnetic field is non-uniform outside the magnet, and it goes towards it. And so now I'm going to heat it. It will take a while, because 770 degrees centigrade is not so easy to achieve. The three most common ferromagnetic materials are cobalt, nickel, and iron. Nickel has a Curie point of only 358 degrees centigrade. So if this were nickel, if this were nickel, now you like that, huh? I think I need a strong hand. A strong hand is coming.
A fail video. Yeah.
Okay, I think I fixed it. I'm a big boy, I did it myself today. I lost my pen, but that's a detail. Okay, let's try again. So I'm going to heat it up, and I was mentioning that nickel has a Curie point of 358 degrees centigrade. So that's quite low. This is 770. Cobalt is 1400 degrees Kelvin, Curie point. Gadolinium, very special material. Gadolinium is ferromagnetic in the winter, when the temperature is below 16 degrees centigrade, but it is paramagnetic in the summer, when the temperature is above 16 degrees centigrade. Beginning to be red hot now.
So for that would be when it turns to a liquid. It's kind of a weird, it solidifies, at 30 degrees or 40 degrees or whatever, 50, 60, no, I think, yeah, it's like, it's right around room temperature. You just go a little lower than room temperature, it's a solid. A little above room temperature, it's a liquid.
770 degrees centigrade, you expect some visible light in the form of red light. There it goes. And now,
alright, so watch that it's swinging. Okay, so there's still a strong magnet. The magnet, he showed that when the nut is just dangling straight down, the magnet's strong enough to pull it over. So clearly it's swinging now, and you don't see any interruption in its swinging. You don't see any any change in it, like some kind of, like, the magnetism of the, it swings into the magnetic field, that it's repelled, or that when it swings into it it's attracted. You really just don't see any evidence that it's paramagnetic.
I'll keep it heating. I will keep the torch on it so that you can see that indeed it's no longer attracted by the magnet, and the moment that I stop heating it, it will very quickly cool. It will become ferromagnetic again, and it will go back. Just watch it. There it goes. So now it's against ferromagnetic. So the transition is extremely sharp.
So, I mean, I don't want to just say they make up some of this stuff, but I think they just make up that it becomes paramagnetic. Nobody's going to be bothering playing with it at 700 degrees, so everybody just assumes, yeah, sure, that's what we'll say. But I don't think it really does.
All right. Okay. So paramagnetic materials, as I mentioned several times, in general cannot hang on a magnet. The attractive force is just not enough. To hang on a magnet, the force has to be larger than...
Okay, so there is no attractive force, and the only thing you can do, I'll say this again, is stick something onto a magnet. And if you stick it on, it becomes part of the magnet, essentially. So if it's conductive, if it can electrically bond, it will acquire the same kind of, it will be part of the structure. And so that's a kind of adhesion, but it's not enough to hold it on because it's a weak magnetism that's being created. The surface isn't it's not creating a bunch of dipoles and becoming a magnet. It's just becoming surface is becoming magnetized, and that surface pressure isn't enough to hold its mass, but it's enough to make it stick a little. But it's only when you've stuck it on something that it sticks. Before you touch the surface, it's repulsive, just like charge. It repels until you hit it, and then it becomes the same thing, and then it repels. But it's, you know, it sticks and then becomes part of
its own weight. And diamagnetic materials is of course completely out, because diamagnetic materials are always pushed towards the weak part of the field. It's only paramagnetic materials and ferromagnetic materials that experience a force towards the strong part of the field if the field itself is not uniform.
All right, so again,
now there is one very interesting exception.
I just don't know how that can be defended, because we've seen it with the piece of aluminum flying off the magnet, repulsive force. You know, these other experiments, certainly other experiments in other videos you can go watch, where you push a magnet into paramagnetic material and it creates a repulsive force, not an attractive force. I don't think there's any examples of where you have paramagnetic material and you run it by a magnet at a velocity and it moves into the magnet. It does the opposite.
And I want to draw your attention to this transparency here. Look here at oxygen at 1 atmosphere. Oxygen at 1 atmosphere and 300 degrees Kelvin has a value for psi of m, which is 2 times 10 to the minus 6. But now look at liquid oxygen at 90 degrees Kelvin. That value is 1800 times larger than this value. Why is that so much higher? Well, liquid in general is about 1,000 times denser than gas at 1 atmosphere. So you have 1,000 times more dipoles per cubic meter that in principle can align. And so clearly you expect an immediate one-to-one correspondence between the density, how many dipoles you have per cubic meter, and the value for psi of m. And so you see indeed that this value is substantially larger. The reason why it is more than a factor of 1,000 higher is that the temperature is also lower. You go from 300 degrees to 90 degrees. And that gives you another factor of 2. Because when the temperature is lower, there is less thermal agitation, and so the external field can align the dipoles more easily. And so that's why you end up with a factor of 1800. Even though this value for psi of m is extraordinarily high for a paramagnetic material, notice that the field inside would only be 0.35% higher than the vacuum field.
So again, this field inside thing is, I think just useless rhetoric, but fine, whatever. This is an example of again, the oxygen isn't really going to be attracted to the magnet. What you're going to see is that it's clinging, and it'll create a gap between the magnets, so it'll essentially just extend the magnetism out and be stuck between the points of a magnet, but you haven't really demonstrated that the oxygen is attracted. You've poured it right onto the surface of the magnet, and by doing that, you didn't pour it in between the magnet, you didn't pour it on one pole of a magnet, you poured it right on top of the magnet.
Because if psi of m is 3.5 times 10 to the minus 3, that means that the field inside is only 0.35% higher than the vacuum field. But that is enough for a liquid oxygen to be attracted by a very strong magnet, provided that it also has a very non-uniform field outside the magnet. And
So again, this non-uniform thing, this garbage talk. I mean, it couldn't be more uniform and predictable and precise and mathematically whatever. I mean, to say it's non-uniform just doesn't make much sense.
So the force with which liquid oxygen is pulled towards a magnet can be made larger than the weight of the liquid oxygen. And so I can make you see today that I can have liquid oxygen hanging from a magnet. And that's what we're going to do here.
It really isn't, because he's going to have both poles of the magnet, and he's going to pour, and they even have the thing built so they can just pour it right on the surface of the magnet. And so he's not going to be pouring a little stream in between the poles. But I mean, even if you took away one of the poles, would be a better experiment. Just pour the liquid next to the magnet and see if the liquid moves into the magnet or moves away. And my prediction would be it would move away if you don't touch the magnet.
Making sure I have the right setting. This is it. So we're going to have some changes in the lights. So there you see the two magnetic poles. It's an electromagnet, and so we can turn the magnetic field on at will. So here are the poles of the magnet, and the first thing I will do is very boring. I will throw some liquid nitrogen between the poles. Now I don't have the value for liquid nitrogen there, but nitrogen is diamagnetic, so it's not even an issue. Diamagnetic material is pushed away from the strong field. So even though the value for psi of m will be very different for liquid nitrogen than it is for gaseous nitrogen, it doesn't matter. So certainly it will be pushed out. So that's the first thing I want to do, just to bore you a little bit. Because I have to keep you on the edge of your seat before you're going to see this oxygen which will be hanging in there. So let's first power this magnet. I hope I did that. Yes, I think I did. And here comes the liquid nitrogen. Boring like hell, it just falls through.
Didn't film that one too well, you know, but yes.
Now comes the oxygen. Liquid oxygen.
So as you can sort of see, he just pours it, bounces all over the place, it gets caught between the two magnets, the pieces are clinging and they just fill the gap. Like a surface tension almost. Just like kind of how charge works. Like I said, the positive and the negative things will attract each other. When they hit, they'll commune and become the same charge, and then they'll repel each other. Same kind of effect. Repulsive until they hit, and then it clings.
It's hanging in there. I challenge you, you've never in your life seen liquid hanging on a magnet. You can tell your parents about it, and of course your grandchildren. It's hanging there. I'll put some more in. Make sure I have the right stuff. Yeah.
So it's not really hanging, it's just extending the magnetism further out and further out. It's creating a conductor of magnetism, so to speak. It's creating something that can make the magnets comfortable together. It's filling an electrical gap almost.
Put some more in. There is liquid oxygen. When I break the current, it's no longer a magnet. It will fall, of course. Don't worry, you'll get more. Who has ever in his life seen a liquid hang on a magnet? It's paramagnetic, it's not ferromagnetic, but because the density is so high and because it's so cold, the value for psi of m is high enough that the force on it is larger than its own weight. If you do this with aluminum, not a chance in the world. Aluminum will not hang in there, even though aluminum, as you can see there, is paramagnetic, but the value 2 times 10 to the minus 5 is way too small, and it will not stick to a magnet. Okay, you have something to think about. I'll see you Friday.
Alright, so fundamental disagreements about what paramagnetism is, and maybe it'll come up in the next videos. Again, demonstrations where I'll just point out, see here he's saying it's a repulsive force and blah blah blah. And this really can't be a phase issue. I mean, some of the experiments using AC currents and some use DC currents. But it really doesn't matter. The magnetism's turning on and off. The paramagnetism is reacting as the fields change, and it's doing the same thing, and that's why it maintains repulsiveness. So, yeah. There's something wrong with this video. It's just wrong, I think. So, till the next time and such. A little bit shorter. 25 minutes. Yay. Anyway. Till next time. Uh-oh. Boy.